Up to this point, we have derived an analytical model for the standard pinhole camera and described the process of calibrating this model. At this point, we can relate the coordinates of points in the image to the robot's 3D environment. Today, we're going to consider the challenge of identifying the small set of salient points present within high-dimensional images. As an example, consider a capability that is critical to self-driving, estimating the geometry of a vehicle's lane. A common approach to this problem involves first detecting the white and yellow lane markings in the images streamed from the car's forward-facing camera. The lane markings comprise a very small percentage of the pixels in the image, and detecting them is like finding a needle in a haystack. Image filtering allows us to more efficiently find these needles. Image filtering refers to a family of operations performed on a small neighborhood of pixels as a means of enhancing an image. This may involve amplifying specific aspects of the image while suppressing others. Consider lanes, which are brightly colored against a dark background. We can detect lane markings by amplifying pixels that differ in color compared to their neighbors. We are going to generate a new version of the image, where each element is a weighted sum of the surrounding pixel values in the original image. This weighting is referred to as the filter kernel, and is represented as a normalized one- or two-dimensional array that is typically much smaller than the image. We can achieve different effects by choosing different kernels. Importantly, we use the same set of weights everywhere in the image. Mathematically, we formulate linear filtering as a convolution, whereby we slide the kernel over the image as we compute the weighted sum at each location in the output image. This procedure is identical to that of image correlation, except that the kernel is flipped left to right and top to bottom. Note that there are different strategies for what we do at the image borders, where the kernel extends outside the image, but we will leave that for later. As a mathematical construct, convolutions exhibit a number of key properties. Convolution is a linear operation, meaning that we can apply them separately to images and then sum the results, or apply the convolution once to the sum of the two images. Convolution is shift and scale invariant, and also associative, which means that several convolutions applied one after the other is equivalent to a single filter. Now, before we look at the effects of different kernels, it is worth pointing out that the process of acquiring an image can itself be thought of as a convolution. Recall from our derivation of the pinhole camera that as we enlarge the aperture, more light rays reflecting off different parts of the object will strike the same location on the sensor. The result is a blurred version of the ideal image that would be formed if each ray struck a unique pixel. Suppose that the aperture is a circle with a diameter of 5 pixels. In this case, we can think of each pixel in the blurred image as being an average of the 21 neighboring pixels in the ideal image. This corresponds to a 5x5 kernel, where all but 4 entries have a normalized value of 1. Convolving the ideal image with this kernel gives rise to the blurred image. Perhaps the simplest choice for a kernel is the impulse function, that is 1 at the center and 0 everywhere else. Convolving an image with the impulse kernel results in an output identical to the input. Consider a slight variation in which we set the center element to 0 and the one to the right to 1. We flip the kernel and then convolve by sliding it over the image and computing the weighted sum. The effect is that each pixel is replaced with the value of the pixel immediately to the left. This results in an image that is shifted to the right by 1 pixel. Another popular kernel is the box filter, where the unnormalized value of each entry is 1. Convolving an image with the box filter results in a blurred version of the image. In practice, we typically use a larger kernel, which results in more noticeable blurring. At this point, one question that you may be asking is, why would we want to blur the image? To answer this question, it is important to realize that ideal images are exactly that. They're ideal. Real images are corrupted by noise, in part as a result of the acquisition process, which introduces noise through quantization effects and analog to digital conversion. Much like we did for edge detection, a common strategy for extracting specific signals from an image is to compute the numerical derivatives of local pixel intensities. These derivatives will amplify noise, suggesting the presence of signals that aren't actually there. One way to reduce noise is to average it out by convolving the image with a box filter. The resulting image has lower noise levels at the expense of a loss of some detail. Applying the same intensity gradient kernel to the blurred image results in much cleaner edge detections. However, box filters can introduce artifacts into the image by exciting high-frequency components. In practice, Gaussian kernels are typically used to reduce the amount of noise in an image. Unlike a box filter, a Gaussian kernel weighs pixels near the center much more than those farther away. Gaussians have infinite support, while kernels have finite support, so we fix their size and normalize so the weights sum to 1. The choice for the standard deviation of the kernel affects how quickly the weights decay, and in turn the amount of blurring. As we increase the standard deviation, pixels are encouraged to resemble more distant neighbors. As a result, increasing the standard deviation results in an increased amount of blur. Besides being less likely to introduce artifacts, Gaussian kernels exhibit a few properties that improve their usability. For one, convolving two Gaussians results in another Gaussian whose standard deviation is equal to the sum of the standard deviations of the original kernels. This means that we can achieve the effects of heavy smoothing by repeatedly smoothing using a small kernel, which is more efficient. Second, 2D Gaussians can be expressed as a product of two one-dimensional Gaussians. As a result, we can perform a 2D convolution by performing two 1D convolutions. This is an example of a kernel that is said to be separable. If k is the width or height of the kernel, 2D convolution involves k-squared operations per pixel. However, we can reduce the cost to 2k operations per pixel if the kernel is separable. Exploiting these efficiency gains is important, considering that we may want to process images that are streamed at 30 frames per second from multiple cameras. By choosing the right combination of filter kernels, we can enhance images in diverse ways, allowing us to control which signals to amplify and which to suppress. Next, we'll describe how we can use image filtering to extract information about a robot's surroundings from an image stream.